Okay, today we're going to continue working with the definite integral, okay, and what we labeled last time is the fundamental theorem of calculus. And we're going to look at how that fundamental theorem of calculus actually could give us the area under a curve. Okay, now when we talk about area under a curve, when we talk about curve, what we're talking about is some kind of function, right, or some graph of a function. Okay, in this example, our graph is just a horizontal line, right, which is y equals 5, or f of x equals 5. So that is our curve, and we want to look at finding the area underneath this curve for x greater than or equal to 1, less than or equal to 6. So if we marked off that area, it would be greater than or equal to 1, less than or equal to 6, would be right here. Okay, now that's basically a square, right? So if we wanted to find the area of it, we could just, again, from 1 to 6 is going to be 5. From 0 to 5 is 5. So to find the area, we could say 5 times 5 times 5 is 25. So the area under this curve is 25 units, right? We're not sure what those units represent. But fairly straightforward, right? Pretty simple. Okay. Get a little bit more complicated and give us a line that's not horizontal, right? So now this curve is the linear equation 2/3 x plus 1. And here we have that graphed. So f of x equals 2/3 x plus 1. And we want to find the area underneath this curve for x greater than or equal to 3, less than or equal to 15. Okay? So if we want to mark that off, so here we have 3, here we have 15. Okay. Actually, let me make sure about that. Yeah, okay, and that actually goes up to this point right here. Okay, so if we want to find the area under this curve, a little more complicated, right? It's not a really simple shape. But one way to do it would be to kind of mark off, well, this is a rectangle. So we could kind of find the area of this rectangle. And then here we've got a nice triangle. So we could maybe find the area of this triangle, right? And then add those together. Okay, and actually that's pretty straightforward. So if we looked at the base of the rectangle, 3 to 15, got a base of 12. The height here is 3. We know a rectangle would be base times height. Again, we get 36 on the rectangle. Our triangle, again, my graphing here is a little bit off, I guess, from the markers or whatever. But just trust me on this. The area of this triangle is also 12. Okay, so it again goes from 3 to 15. And then the height up here, if it was graphed accurately, is 8. Okay, so area of a triangle is 1/2 base times height, and that would give us 48. Okay, so to get the entire area under the curve from 3 to 15, we could add 48 plus 36 and get 84. Right, so that's our area under the curve. Now, again, like we've done a lot in this class in calculus, this one's a pretty easy one to find a area under the curve, right? Not as easy as the previous example, but again, we're looking at the formulas and the solutions for finding the area under, you know, possibly way more complicated curves, right? So, you know, where you can't break it into shapes and, you know, use counting and, you know, geometric formulas, that kind of thing. So a more advanced way to do it using calculus is actually to apply the definite integral. And we'll see how that can actually give us the area under this curve. So again, I've got the same curve, same graph. I'm going to, again, try to find the area for x greater than or equal to 3, less than or equal to 15. And I'm going to do this by finding the definite integral from 3 to 15 of 2/3 x plus x, and then finding that antiderivative with respect to x. So I've got the dx here. So in order to do that, we consider that having a exponent of 1. We add 1, we get 2, we divide by 2. This becomes 2/6 x squared, which again we know we simplify it to 1/3 x squared. This is 1 x to the 0 power, add 1, divide by 1, we get plus x, right? So here's our antiderivative, and we want to find the definite integral from 3 to 15. Okay, so again, this is just like we did on homework. So we're going to find f at 15 minus f at 3. So if we plug in 1/3 15 squared plus 15, 15 squared divided by 3 gives us 75, plus 15 gives us 90. F at 3, again, we plug it in, we get 1/3 times 3 squared plus 3, and we get 9 divided by 3 is 3, plus 3 is 6. So we subtract, and we get 84. So again, the same area we found by cutting the shapes, you know, and using area formulas, okay? Now, I want to talk a little bit, again, I'm not going to go too much into theory here because we haven't looked into that this whole year, but I do want to talk about how this works in a very broad sense. So here we have kind of the setup or the formula for definite integral, okay? And if we rewrote that as a limit, okay, if you looked at the calculus book, you'll see this. This can be thought of as the limit as n approaches infinity of the summation from 1 to n of f of x times delta x. Okay, now I don't expect you to understand this notation, okay? But what I do want you to understand or kind of have a general idea of is f of x times delta x. F of x always represents y, right? The y value, and delta x is exactly what it means, delta x. So if you were talking about y times x, you're actually, that kind of represents the area of maybe a rectangle where the difference in your x is your delta x, or the base of it is delta x, and the height of it is the y value. Okay, so what this is showing is that we're taking the this sign symbol right here is a summation sign symbol, which just means adding up all these values from 1 to infinity. Okay, so what this represents is that we're taking the limit of the area of an infinite amount of rectangles underneath this curve, okay? And by taking the limit as n goes from 1 to infinity, this value represents the area of these rectangles, and we're making them infinitely smaller rectangles and taking and adding their area together, okay? Now, we're not doing that actually, but the definite integral represents taking that limit of all those rectangles and adding them together and making them smaller and smaller, okay? So again, not a really eloquent explanation by me, but I do want you to understand that taking the definite integral is the equivalent of adding the area of infinitely smaller and smaller and an infinitely number of rectangles underneath the curve, and that's kind of how the magic happens. Let's say, okay. So again, I didn't want you to get through calculus class without seeing at least how this infinite number of rectangles can be thought of is eventually giving you the area. Okay? All right, so how are we going to use this? What are our problems going to look like? Okay, so first of all, the fundamental theorem of calculus, we've got it right here. Just again, if I read this to you, so if f of x is continuous and f of x is greater than or equal to 0, so our function is greater than or equal to 0 on the interval x greater than a and less than b, then the region under the curve, y equals f of x, above x greater than or equal to a and less than or equal to b, has this area. And again, this area formula is just taking the definite integral of that function from a to b. Okay, so let's take a look at some applicable problems. So problem number 1, find the area of the region under the curve y equals x squared plus 6x plus 7 between its x-intercepts. Okay, so let's take a look. Here is a graph of that curve. So we want to find this area right underneath the parabola, and we want to find it between the x-intercepts. So how can I find the x-intercepts? Well, I could look at it on the graph, and I can see where it is actually -1 and 1, 2, 3, 4, 5, 6, 7. But what if I'm not really sure about that? How else could I find the intercepts? Well, we can see the intercepts are where the y value is 0, right? So if we do this algebraically, we set it equal to 0 and solve, right? And in order to do that, we have to factor. So what I'm going to do first, I don't like factoring with a leading negative. So I'm going to multiply the whole thing by -1 and get x squared minus 6x minus 7. And now I'm going to factor what multiplies to -7 adds to -6 would be +1 and -7. And then when we solve that, we get -1, 7. So here I've just used algebra to verify what my graph told me. So to find the area under the curve of this parabola between its x-intercepts of -1 and 7, I simply take the find the definite integral from -1 to 7 of -x squared plus 6x plus 7. Okay, so continuing to do that, I add 1, I get 3, I divide by 3, so I get -x to the third over 3. I add 1 here, I get 2, I divide by 2, so plus 3x squared plus 7x. And again, I'm going to evaluate that from -1 to 7. Okay, so I'm going to find f at 7, subtracted from f at -1. Okay, so again, let's plug this in on our calculators. Again, like I said last time, the biggest mistake people make with this oftentimes is the plugging in. So I'm plugging in 7. So I'm going to say -7 to the third divided by 3, and then plus 3 times 7 squared plus 7 times 7. And I get 81.66666, so I'm going to call that 81.67. Now I'm going to find f at -1, and again, this one I can do, I'm going to kind of do this by hand. So -1 cubed over 3 plus 3 times -1 squared plus 7 times -1. -1 cubed is going to be -1 times -1 gives me +1, so I got 1/3 plus Negative 1 squared is positive, so plus 3, and then minus 7. And that ends up to give me negative 4 plus 1/3. So that actually gives me negative 3.67. Okay, so you could plug that in on your calculator if you wanted to. So we were taking 81.67 minus negative 3.67, which becomes plus, and we get 85.34. Okay. Now, if you notice, so this gave us a positive number, right? Of course, is what you'd expect. But when you're talking about area, just like you're talking about any measurement, area always has to be positive, right? Because you never could have a negative area, just like you can't go a negative distance. So what this little box is reminding us that even if the function is less than or equal to 0, that goes underneath the line or underneath the x-axis on a given interval, then the area is always going to be the absolute value of the integral. Okay, so what happens then is we go through all of our process and we find our values and we do the subtraction, but on the final answer, if it is negative, then we make it, then we take it, the absolute value of it. Okay, so for instance, let's look at the next one. So here, we're going to find the area of the region between the x-axis and the curve. So here's where we get, when we talk about the area under the curve, you really want to think more about it being the area between the x-axis and the curve. So in this case, if we're looking from 1 to 3, okay, so here, a bit different of a variation, it went ahead and gave us, instead of saying between the intercepts, it's just saying we just want to know the area of the curve between 1 and 3. So that would be here to here. So we're trying to find the area of this little section, okay? So those y values are underneath the x-axis, and we're going to see where we're going to end up with a negative value, but our final answer is going to be positive. So let's see what happens here. So we're taking the area from 1 to 3 of the curve, x squared minus 3x, and we're taking the antiderivative with respect to x. So we're going to, again, find the antiderivative. So we add 1, get 3, divide by 3, so we get x to the third, divided by 3. Here we add 1, we get 2, we divide by 2, so we get minus 3/2 x squared. Okay, and we want to evaluate this again from 1 to 3. So we want to find the value of f at 3 and subtract it from the value at f at 1. Okay, so I'm going to say 3 cubed over 3 minus 3/2 3 squared. So again, let's plug this in. So I've got 3 cubed divided by 3 minus 3/2 times 3 squared. And that gives me negative 4.5, which again, if we'd done this by hand, oh, I don't like that spinning. Okay, if we'd done this by hand, we would have gotten what, 27 over 3 minus 27/2. So we still have to do some conversion. But this value is negative 4.5. Okay, and then minus, we've got 1/3 minus 3/2, basically, right, with the positive x of positive 1. And that's going to give us a negative 1.167. So when we subtract negative 4.5 minus negative 1.167, we end up with negative 3.33. Okay, now an area, as I said, cannot be negative, but you will end up getting a negative number when the function falls below the x-axis. So what we do in this case is we do all the calculations as normal. But when we get to the very final answer and we say it's negative 3.33, then we take the absolute value of it and make it positive. Now, I'm making a big deal out of this because of lots of common mistakes is as soon as you get a negative value, like right here, or maybe right here, girls want to go ahead and make that positive. And you don't want to do that. You want to keep everything exactly how it turns out until your very final answer. And when you're ready to say this is the area, that is when you want to take the absolute value of it if it is negative. Okay? All right, now I want you guys to try this next one, and we'll come back and check. So actually, go ahead and do the next two. So go ahead and find area under this curve between the x-intercepts. So we'll need to find those x-intercepts, and then find the area under this curve between -1 and 3. Okay, so hopefully you guys did these on your own, and let's see what we got. So again, we had to find the x-intercepts. Oops. For this curve, right, which we can tell is a downward facing parabola. And the x-intercepts would be 6 to -6, so that is our a and our b value. We take the antiderivative, and we get negative x to the third over 3 plus 36x. We evaluate it at positive 6, and we get 144. Evaluated at -6, and we get negative 144. And so again, be tricky here. We're taking 144 minus a negative, so we end up adding 144 to 144. We get 288. Okay. And again, when you think about, okay, anyway, okay. So let's look at the next one. Again, another parabola, right, upward facing. So this is upward facing. However, when you think about this graph, it is upward facing at 2. So it's not actually, even though it's upward facing, it's not going below the x-axis. So that's why we end up without not getting a negative value here, as I thought. Okay, so we take the antiderivative, and we're going to evaluate it from 3 to -1. So we find f at 3, plug it in, we get 15. We find f at -1, plug it in, and again, I did this kind of both ways. As a fraction, I ended up with -7/3, or -2.33 if you use a decimal. And again, we're taking 15 minus a negative value, so we end up adding, and we get 17.13. So again, if you were looking at this, a rough sketch of the graph, we were looking at the area between the x-axis and the curve from -1, which is like maybe right here, to 3. Okay, so the area we're looking at, or we're computing, is actually this area right here. Okay, so from -1 to 3. Okay, if we looked up here, if we looked at this area, again, you don't need to graph it. I'm just trying to give you all the visuals to what this looks like. This is -x² plus 36, so this is going way up to 36, but it is symmetric around the x-axis. So this is up at 36, and we are finding the area from -6 to +6. So we're finding this area. So you can kind of see where when we ended up getting the 144 plus 144, we've got two equal areas here. That is what they're, that we're adding those together. So, okay, so anyway, just to kind of give a heads up as to what it looks like graphically, okay? So what I want you guys to do is the worksheet that I'll talk about.